Welcome everybody to our webinar today on water-soluble fertilizers. I can see that we've still got a few people that are in the process of logging into the system. So we're going to go ahead, wait about a minute or so, and then we will get started here shortly. Thanks for your patience. Okay, welcome everybody to our webinar today, water-soluble fertilizers. The future is crystal clear. My name is Jill Browning and I will be your moderator for today. I just want to make a couple quick notes or housekeeping notes before we get started today. For audio, there are two different options. Hopefully you should be able to hear me now. But I do want to just make a quick note that there are two different ways to connect. You are able to connect via your computer audio, or you can also connect through the phone line. So for any issues, if you have anything that pops up throughout the webinar, if it for some reason disconnects, I just want to let you know that there are two different ways, so feel free to switch between those two different options should you have any issues. And then also one quick note, just to mention that due to the number of attendees that we have on the line today, we have gone ahead and muted the participant lines, but please don't worry about, we do want to make this as interactive as possible. So with that, there is an option to, or we invite you to ask any questions that come to mind. There is a questions panel that is over to the right-hand side of your control panel. So feel free to type any of those questions that come in, and we'll try to get to as many of those as possible as time allows. One quick note as well, we have gone back through the last couple years of the webinars that we have created and presented, and we have put those available on our website over at www.veoliawatertech.com. So feel free to go over to that site, take a look at it, and register and watch any of those on-demand webinars that may be of interest to you. One other quick thing is we do value your feedback. At the end of today's webinar, there will be a quick survey that we kindly ask that you complete. It should take no more than 1 minute. And for those of you that do complete that survey today, you will be entered into a drawing to win a $25 Amazon gift card. So if you are selected for that as the winner, we will follow up directly with you at the conclusion of today's webinar. Okay, one quick slide about Veolia, and then I will introduce our speaker today. Veolia Water Technologies, we are a leading company within water treatment. We've got about 9,500 employees worldwide, serving a variety of different clients with both municipalities as well as a variety of different industrial clients. We do have three key main areas of focus. Technologies, we've got over 350 proprietary water treatment technologies and processes, as well as focusing on projects and services. So with that, I will like to introduce our speaker today. Sana Boulabier is a process engineer for Veolia Water Technologies and is based in Chicago, Illinois. She specializes in the design of NPK fertilizer systems utilizing HPD evaporation and crystallization technology. And today she will be talking with us about water-soluble fertilizers. Sana, are you with us today?
Yes, I am. Thank you, Jill. Good morning, everyone. Welcome our clients, our partners to this webinar. So I'm very pleased to be your speaker today and to talk to you about a little bit about crystalline water-soluble fertilizers. So as Jill mentioned, I'm a process engineer at HPD Evaporation and Crystallization. I'm located at Chicago, but we have 200 people in HPD, a business unit. Some of them are in Chicago and some others are in Spain, but we have also other sales managers located all over the globe in Australia and China, in South America and Europe. So we are serving industrial clients all over the globe. So just to give you a quick idea about HPD for those who do not know us. So HPD, as I said, is 200 people. We are focused on evaporation and crystallization systems across multiple industrial and chemical markets, such as the salt market, metals and mining, lithium, pulp and paper, oil and gas, and fertilizers, of course. And that's why we are having this webinar today to talk about fertilizers. So HPD, in HPD, we don't provide equipment only. We provide engineering equipment and other services. So for engineering, we provide basic engineering and detailed engineering. As I said, equipment, we have a global sourcing for that. And we have other services such as after sales, system troubleshooting, commissioning, startup, supervision, and so on. So I think what makes, or basically what is our main differentiator as a big player in the evaporation crystallization business is our advanced technology and process design capabilities. So we have the ability through our process design team to develop a comprehensive flow sheet development. And because we have a very big R&D center located in Chicago, we can validate this flow sheet and we can test many things. We can do bench scale testing to confirm physical properties and solubilities and to actually test the process, but we can also demonstrate the process on a pilot scale, and we can do corrosion testing, we can do in-house analytical testing. So it's actually very nice because we don't really need any external analytical lab for that. So I think this is a great thing and gives us a lot of flexibility. And it's also the great thing about being part of Veolia is the access to all of these technologies, or all of these more than 350 technologies that Veolia Water Technology allow us to access to. So we can sometimes provide a very full process, an integrated process to our clients. So today we will talk about fertilizers and more specifically the future of water-soluble fertilizers. I think in these days where we have where the whole world is locked down due to COVID-19, it's important to talk about the future. It's important to focus and step back actually and think about what is essential. So what is essential is actually, as it has always been, actually it's boosting agriculture productivity. I think this is important for the global agriculture industry for many reasons, because of course, because of population growth, because of higher food demand that we are having more and more, but because also the whole world is changing towards requiring more high value, for let's say high value foods, not only eating carbs and rice and wheat, but everybody is leaning towards eating more proteins, eating more fruits and vegetables. And I think like because people are having higher incomes, and this class of affluent people or more rich consumers is increasing. You can see it in the graph on the right, but also because with all the social media going on right now, if I'm eating like avocado, you want to eat avocado. If I'm having building muscles and eating more proteins, you want to also eat protein. So this trend is increasing a lot. On the other hand, the agriculture industry, let's say the agriculture industry and globally, it's having a lot of pressures. The pressures are coming from basically the burning environmental issues that the world is experiencing. I don't need to remind you this, but I think you know all the problems related to the low or the less land or arable land, let's say, also the less water or the problem of water scarcity that the world is suffering from. And the agriculture industry is a contributor and a casualty of this problem. And it's a centerpiece in this problem. So given these constraints, what the agriculture industry need to do, what farmers need to do, they need actually more with less. They need to boost productivity, but also they need to care about the environment and to, let's say, use less land and less water. So that being said, we need to gain efficiencies. And we cannot do that except if we use smart agriculture techniques. And that's why all these fertigation techniques, foliar feeding, precision farming, and irrigation are increasing a lot recently, and they are expecting it to increase more and more with the increase in need to boost productivity. So these smart agriculture techniques actually they really need to we really need to have a better fertilizer management so that we can use them, but at the same time we can reduce the nutrient loss and have a better water management. So advanced farming techniques, including fertigation, foliar feeding, and precision farming, they cannot work with conventional or traditional fertilizer products. That's why we need, or they need to have advanced fertilizer products available in the market so that they can really achieve their goals. So, and this is where the fertilizer market, where we can see the fertilizer market role. The fertilizer market needs to provide these advanced fertilizer products, but the market itself has its own challenges and has its own limitations. Let's go through them very quickly. Some of you, I'm sure you know what I'm talking about here, but the fertilizer market is suffering from lower prices, lower price of fertilizer products. So the fertilizer producers, they need a differentiated product portfolio to increase their growth, or let's say to have a profitable growth. Also, fertilizer producers, they need to control cost. Raw material prices are increasing. The process of production of fertilizers are energy intensive. So the producers, they need really to deploy strategically CapEx in order to control these costs. On another hand, the fertilizer market is suffering from a lot of societal pressures. They need to cut waste, they need to reduce consumption, and also they need to reduce emissions. So given these constraints, the fertilizer producers are, let's say, living a big dilemma: how to respond to farmers' needs, boosting productivity in a very sustainable way, while overcoming these production challenges and keep the cost down and increase profitability and care about the environment and the resources. The answer to that is the use of crystalline water-soluble fertilizers. So the crystals are our hope. So why the crystals are, let's say, our hope in achieving these two goals? First of all, because crystals are a high value fertilizers. They have the highest purity. They have the lowest water insoluble amount that basically the water insoluble can have a big impact if they are there into clogging spraying systems and dosing devices that are, for example, used in fertigation or foliar feeding. They have very low amount of impurities, including sodium, chlorine, or heavy metals. Also, they can be produced in a consistent and a predictable size and shape, and also they are easier to transport. Also, the crystalline water-soluble fertilizers, they can help the fertilizer producers overcome their hurdles or their, let's say, challenges in three different ways. So the first way is they help into the diversification, achieve the diversification role. If you remember, I said at the beginning, the prices of fertilizers are getting high, or like actually it's getting down. So the fertilizer producers, they need to have a big portfolio of product to differentiate, to have a product differentiation with higher margins. Also, the crystallization process enable to control costs because it allows to have more flexibility in raw material or feedstock and to have a more efficient production. And the last bullet point is sustainability. So the production of crystals allow many times to valorize or waste streams. So what is the key? How can water-soluble crystalline, in a crystalline form, let's say, achieve these targets and help fertilizer producers? The process of crystallization is the key behind all this. So let me first give you a quick idea about crystallization process and how does this work. So the crystallization process is a separation process that, let's say, separates a solid phase from a liquid phase. So the thermodynamic equilibrium between the solid and the liquid phase is driven by the solubility curve that you can see on the left of the slide. So you can see there is a stable zone, metastable zone, and unstable zone. Basically, when the solute, which is the product we want to crystallize, the solute is in a solution, which is typically water. So when the solute is at a certain condition of composition and temperature that is above the solubility curve, so that is in the stable zone, it is in liquid phase. When the solute is supersaturated, so either we play with temperature or composition, and we go below this solubility curve, it is supersaturated, and we can get crystals. The crystals are produced from the solvent or from water. So basically, we can go to this. Basically, actually, supersaturation is the driver for this crystallization process, and the supersaturation can be achieved in two ways. So the first way is evaporative crystallization. When I say evaporative crystallization, means that the solution becomes supersaturated as a result of evaporation of water. So we evaporate water, the solute composition increases, we go below the solubility curve, it's supersaturated, and the crystals are released. The other way of crystallizing is by cooling crystallization, and it's usually applicable for compounds with relatively steep temperature-dependent solubility. So for these cases, when we go lower in temperature, we also go below the solubility curve, and then the system is supersaturated, and we get our crystals. So the crystallization process allows to let's say has two goals or two roles. The first role is to produce the crystals, of course, produce crystals with a consistent and controlled shape and size. First. Second, it is a purification process, and this is actually what makes the crystallization a very powerful technique is the power of purification that has. So the purification means that we can reach very low impurities in the final crystalline fertilizers. And when I say impurities means even water insoluble impurities that sometimes we can have the fertilizer producer can specify in their spec of final product. So just to give you an idea about how a basic crystallization flow sheet look like, this is a simple example where we have in the center of the flow sheet, we have the crystallizer vapor body, we have a crystallizer heater that will bring the energy that will drive the crystallization process. The feed is fed to the crystallizer, and then the slurry leaves the recirculation loop of the crystallizer to a dewatering device. Typically, it can be a centrifuge, a decanter, a filter. The crystals, the wet crystals, go out of the dewatering device to a dryer, and the mother liquor separated from the crystals go to a mother liquor tank and then goes back to the crystallizer vapor body. So this is an example of evaporative crystallization. So you can see from the crystallizer, you have vapors going out of the crystallizer. We can achieve reaction here. So we can do reactive crystallization, not only the crystallization. So the feed can be, for example, KOH and phosphoric acid to make MKP. It can be sulfuric acid and ammonia to make ammonium sulfate. So we can make reactions at the same time as crystallization. And the crystallization flow sheet has, we can do many ways for energy recovery and saving. So here, for example, you can see vapors leaving the crystallizer. They are compressed through a compression device. Typically, it's a mechanical vapor recompression, what we are showing here. And the vapors, the compressed vapors, they go to a heater, the heater that drives the crystallization process. And actually, we get water. I mean, the condensed vapors are process condensates, and they are leaving the system as recovered water, and they can be used within the system, the fertilizer complex. So basically, the crystallization flow sheet allows us to recover water, but also to recover energy and to achieve energy savings. Crystallization technologies. So we have different technologies. The technology selection is mostly driven by crystal size requirement. Sometimes it's also by energy requirement, but most of the time is by crystal size requirement. Here in this following graph, we show the three main technologies, and we show, let's say, the crystal size distribution. So for circulation technology is usually used for when we don't need, I mean, the particle size is not that critical, but when we need a more narrow or narrower particle size and larger particle size, we usually go to a draft tube baffle. And if we need to increase it even more, we go to a growth crystallizer type technology. So here are the technologies. For circulation technology is when, as I said, when we don't have any specific requirement for particle size, and it's basically a mixed suspension. Everything is mixed. The recirculation has a slurry. I mean, we recirculate the slurry through using an actual pump through the recirculation. The feed enters the recirculation. We heat the system in this heater located also in the recirculation, and actually the feed is heated in the recirculation loop, and when it enters the crystallizer body, by flash decrystallization occurs. Now when we go to the second type, which is the draft tube baffle technology. In this technology, the recirculation or the agitation is not done through an external recirculation. It is done using a draft tube inside the vapor body. And as you can see, we have a bottom-mounted agitator there. So the supersaturation is driven by the recirculation that is achieved by the agitator. What is interesting also that the agitator allows for less wreckage of the crystals. So we, let's say, maintain the shape of the crystals. Also, the draft tube baffle has a baffled area, so we have an overflow from the baffled area. These are mostly, actually, it's a clear solution having some fines, and this actually clear solution can go to a fine distraction loop, and through a heater we can destruct the fines and dissolve them. So that's also helps to grow more the crystals. The other type of crystallization technology is a growth technology. And you can see in this technology, we have basically more classification. All the bottom part is for retention, and then it actually has basically a fluidized bed of crystals, which allows to grow more the crystals and have a narrower particle size distribution. So this is an idea about what the different types of technologies. If you have questions, of course, you can ask later for details. So I mentioned earlier that what makes crystallization process unique is the fact that it's a powerful purification process and technology. So here I'm showing you how we can achieve this high quality products and how we can achieve this purification goal. So the crystal purity can be controlled and achieved through different things. So the most obvious way, of course, is to play with operating conditions. When I say operating conditions, means temperature, pH. So we can crystallize this product and remove impurities, and then we can play with these operating conditions the way we want so that we can selectively crystallize our product with high purity. Other ways of controlling purity is actually playing with the purge and washing the crystals. I think to better show you the power of purification, let's compare crystallization to another process. So look at the left of the slide where I'm showing granulation process. So the granulation process, you have your feed goes to the granulator is heated by air, the vapor or the water is evaporated, you get air and vapor from the granulator, everything goes to the exhaust air system and everything leaves the system to the atmosphere. And from the granulator, we get fertilizer granules. So here in the granulation process, there is no purification, obviously. There is no heat integration, there is no water recovery, and everything that goes out in the system, actually everything that goes into the system goes out in the system. If you have impurity 1, it will go out, it will go with the granules. So obviously there's no purification. And the granulation process, because there is no heat integration, and it's actually more energy intensive. If you go to the right of the slide, you have the basic crystallization process flow sheet. In the crystallization process flow sheet, the feed enter the crystallization process, the slurry is dewatered, and then the mother liquor are recycled back to the crystallizer. But here, what is interesting is that, first of all, we have a purge stream that is loaded in impurities. The higher is this purge stream, the more diluted the crystallizer system is in impurities. So by controlling this purge stream, we control the concentration of impurities within the crystallization system. Another thing we can do here is the washing of the crystals. So the washing of the crystals can be achieved within the, let's say, the water, the separation device, which can be a centrifuge or a decanter. Here, the washing water will displace the residual mother liquor and the residual impurities that are coming with the crystals. Impurities are replaced with water, basically, and the fertilizer crystals will leave the separation, liquid-solid separation, with a higher purity. So the other thing here, we can see that the vapors leaving from the crystallization, leaving the crystallizer, can be recovered. It can be sent to a condenser, and the process condensate can be recovered. And also the quality of process condensates can be controlled. Other ways to control purity is to perform a second crystallization stage. So basically, the first crystallization stage is similar to what I showed earlier in the previous slide. But once you get these crystals that I called here crystals 1, they are dissolved using mother liquor and some water makeup, or sometimes just water. But we dissolve these crystals, which means that we dissolve the crystals, but also we dilute the impurities coming with the crystals. This means that when we go to the second crystallization stage, we recreate these crystals in an environment that is less diluted or more diluted in impurities. We can also have a purge there, which also allows to control the concentration of impurities. all of this leads to the fact that we can achieve high purity fertilizer crystals when we go out from the separation process. Of course, here we can have washing in the separation process 1, in the liquid solid separation process 1 and the liquid solid separation 2. Also, we can add washing lags to external or internal washing lags to the first crystallization or to the second crystallization stages. The washing lags allow to also displace the impurities and to reach high purity fertilizer crystals. There are so many ways of that, to increase the purity of crystals, and this is all done by the crystallization process. So the crystallization process allow us to it's a flexible and sustainable process. It allows us to produce high value fertilizer products, but not necessarily from very pure feed streams. We can really use low grade streams and use the crystallization to purify and produce high value fertilizers. And this leads to a huge production cost saving, saving in operating cost, and also waste valorization. There are different or a big portfolio of crystalline fertilizers, water-soluble fertilizers available. One of them is here, for example, and fertilizers. One of them, or the most common, is ammonium sulfate. There are also other ammonium phosphate fertilizers, NP. We mentioned here MAP, we mentioned DAP. Hello? So we mentioned MAP, we mentioned DAP, monoammonium phosphate, diammonium phosphate. So for example, MAP is, let's say, a moderately acidic pH crystals. And these crystals, actually, they are very interesting because they can be produced not only from purified acid, but also, let me show you here an example. Yes, so MAP crystals can be produced from not only purified phosphoric acid, but also from merchant-grade phosphoric acid, and this actually brings a lot of value to the fertilizer producers. So here we are showing a very, let's say, classic and traditional way of making MAP water-soluble crystals. So we start from the phosphoric acid production plant to make merchant-grade acid. Merchant grade acid goes to the purification plant where we make technical grade acid, and then technical grade or purified acid goes to the crystallization plant to produce water soluble MAP DAP. Now, crystallization is interesting because it allows us to use a lower grade phosphoric acid. So we can start from the merchant grade and use a crystallization process, use the same raw material, ammonia here, but a lower grade phosphoric acid to produce the same quality water-soluble MAP DAP. Exactly the same quality is achieved through crystallization. An example for MAP production from a low-grade acid is our plant in Tunisia for our client Alchemia. So we use merchant-grade acid. They don't have any purification process in their fertilizer complex, and we can achieve 25,000 ton per annum of MAP production, water soluble with a purity higher than 99%. So it's a 12610 for with water insoluble less than 0.2%, no heavy metals, no sodium, no fluorides, no chlorides. And also we have guarantees on ammonia emission and dust emission, and they were very low. So the process of production of MAP from the merchant grade acid in this process has two crystallization stages using DTB crystallizers that I showed earlier. We have a purge recycled within the fertilizer complex, and we supplied crystallizers, we supplied centrifuges, dryers, screening systems. So let's continue our the fertilizer portfolio just, list. So we have other soluble crystalline fertilizers, phosphate, potassium phosphate crystalline fertilizers. So we have MKP, monopotassium phosphate, dipotassium phosphate, monopotassium diphosphate, and this one actually, the last one, 06020, is very interesting because it's actually called the solid phosphoric acid because it is very acidic. It has a very, very high solubility. It is extremely interesting, especially because it has anti-clogging action to the fertigation equipment. It's also compatible with calcium and magnesium fertilizers, and it's a very interesting potassium phosphate fertilizer product, and can for sure be produced as crystals from KUH and phosphoric acid. Another fertilizer, water-soluble example is potassium nitrate, and also without forgetting all the potassium fertilizers, KCl and SOP, and this is when soils cannot supply the amount of potassium required by crops. We use these crystalline fertilizers. I would like to highlight a little bit more about SOP, potassium sulfate. So this interesting fertilizer product is used when crops are sensitive to chlorides, and it's actually an excellent source of sulfur. It is required for protein synthesis and enzyme function, and it actually can be produced. Again, I want to show you an example of how we can produce the same high value product, but from different sources and different raw materials. This is a slide to show you the different sources we can make to make the same SOP crystals. So we can make SOP crystals through evaporation crystallization using natural brine, using reacted salts. When I say reacted salts, for example, sodium sulfate and KCl, this is the case of one of our last wins with Alkim in Turkey. So we can make SOP. Actually, we make 50,000 tons per annum of SOP crystals from a waste stream, sodium sulfate waste stream. We can make SOP crystals even from pulp and paper mill waste stream, actually from the ash treatment waste stream. We make lazurite, and from lazurite, we make SOP. Also, we can, of course, the more, let's say, traditional way of making SOP is from KCl and sulfuric acid. And actually, HPD is developing a process to make the SOP crystals using these raw materials and to replace the conventional Mannheim process that is energy intensive and very old and energy intensive process. So just to maybe give you more information about SOP from natural brine, the first let's say source I'm showing here in the slide. So SOP from natural brines. SOP from natural brines, when I say natural brines, like we have a lot of types of natural sources. So it can be, for example, polyhalite brine from conventional mining. It can be solar evaporated lake schwannite brine. It can be dry lake kyanite brine. So for all these cases, we have references. I want to talk to you today about the Compass Mineral reference, where we produce SOP crystals from solar evaporated schwannite brine, max sulfate, potassium sulfate, 6H2O. So this is one of our last references with the schwannite brine. So we produce 325,000 tons per annum of SOP fertilizer grade with high purity and high product yield. We use draft tube baffle crystallizers that is integrated into the existing system that Compass Mineral has, and the system was operating and actually started up in 2017. The product, the SOP product that we produced, has the name Potassium in the market, and actually the one interesting thing I didn't say here for SOP is that because, especially in natural, when we talk about natural raw materials, is that the product, the SOP produced, can be actually organic, because it's all natural sources, so it can be organic. So basically here we can produce organic grade SOP crystals. So to summarize, today we wanted to really show you how the power of crystallization and how water-soluble crystals are the way to give farmers what they are looking for. Farmers want to boost productivity in a sustainable way. and at the same time use efficiently advanced farming techniques. But at the same time, water-soluble crystals allow also the fertilizer producers find what they are looking for, which is have advanced fertilizers, high value specialty fertilizers with unique purity and solubility profiles. They want a product diversification. They want to control production cost, and they want to manage the waste, and all these can be achieved thanks to the powerful crystallization process and thanks to the crystalline fertilizer products. Thank you for your time.
Great. Thanks, Sana, for that very informative presentation there. I just want to remind everybody, if you have any questions, we had some that came in throughout the presentation today, but just wanted to remind everybody as well, feel free to type over any questions in that questions box in your control panel. So with that, I'm going to open it up to questions now for Sana, and we'll try to get through as many as we can. We've got a few minutes left here in our allotted time. And for those questions, if we don't get to them, we will follow up directly with you afterwards. So feel free to, I believe there's a next slide here with Sana's email as well. So if you think of anything throughout, then feel free to email her directly as well with that. So with that, Sana, I'm going to open up the questions. One question that came in here is, what is the price between water-soluble crystalline fertilizer and granular fertilizer?
So typically the price of water-soluble fertilizer is usually the double of the price of granulated fertilizer. This is, for example, applicable for MAP crystals. So usually the water-soluble MAP crystals are almost the double of the price of MAP granules.
Okay, another question is, can you produce calcium nitrate and magnesium nitrate with crystallization?
Yes. I think I need more information about the feed. But this is something I think we can do. And of course, I need more information about the raw material. Now, the list that I'm showing in the table of the fertilizer portfolios is not, the list is not only that. We have a lot of other products, but the most common are what I presented in that table.
Okay, great. Yeah, if the question asked, who asked the question, if you want to follow up directly with Sana afterwards, feel free to do that as well with that. Another question is, what is the yield that you can achieve for MAP production?
So the yield is basically related to the quality of the acid. So if we are using immersion grade acid, the immersion grade acid has there are so many let's say qualities of immersion grade acids. So I think the yield it can be as low as 30 to 40% if it's a very low quality of immersion grade. It's and it can go up to 90 to 85 to 90% of yield. And the yield, when I say yield, is P2O5 yield. So how much, let's say, phosphate we lose through the purge out of the system. Now we can improve that yield, of course, if it's a low quality immersion grade, and if it's a 30 to 40% is very low, we can do many things to improve that. Can be doing some pre-treatment for the immersion grade. This does not mean purify, do a whole purification for the immersion grade. Means that we can do just, for example, decrease sulfates if the sulfates are the problem, or decrease another specific impurity only by simple pretreatments. And the fact that we are part of Veolia, we have access to a lot of pretreatment processes. So it helps us a lot. So most of the cases we can really go very high in yields.
Great. Another question, and this is actually in regards to alumina refinery plants, I believe, but is it possible to extract carbonate and oxalate with crystallizers?
Carbonate and oxalate with crystallizers. I think I need more information, more specific. I mean, I think I need, if the person who did ask this question, if he can just send me an email and give me more information, I will probably answer and give him the answer by email.
Okay,
Because
great.
I'm
Yeah,
not sure.
he mentioned, yeah,
The calcium,
he will follow
how
up directly with
exactly
you
it is?
there.
Calcium, can we extract calcium and?
Another question, we've got time for just a couple more questions here is, what type of test do you need to do to extrapolate the process to industrial scale?
So depends. So depends on the raw material and the spec of the client. If we have enough information in-house, we can sometimes just skip the test part. But if we have a low-grade raw material or we have very high spec for the final product, we typically do testing. We typically do only bench scale tests, and we are able to extrapolate from bench scale to the industrial scale. And the bench scale tests are usually solubility data, confirmed boiling point elevation, very, 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 let's say physical properties checking and confirmation. And we sometimes also do, when we go to a pilot scale, usually if the client wants to demonstrate, but most of the time we just stay in the bench scale. Sometimes, for example, if we have chlorides, we have any species that can impact the material of construction, we can do corrosion testing. If we would like to confirm the size of we have, for example, guarantee on the size of the crystals, then we'll need to perform also bench scale where we study the crystal size distribution. So it depends on the cases, but we are comfortable usually extrapolating from bench scale to industrial scale.
Great. I think we've got time for one more question here. What is the maximum capacity of a crystallizer? For instance, tons per day, perhaps.
The maximum capacity, I don't think we are limited by really a capacity. You mean the one in one body? Because we have the possibility to have, 2 lines, 3 lines. So it's not usually, actually usually the let's say, for example, some clients, they do want to have prefabricated vessels. So we are limited by a certain size for the crystallizer. Typically it's 15 feet size for the diameter. So we try to stay less than 15 feet for the diameter of the crystallizer. But from a crystallization standpoint, there is no limitation other than the shipment. And then some other clients, they don't have any problem to have field fabricated vessels, so the vessel can go. We have like one of our potash plants in Canada, K Plus has I believe 12-meter diameter crystallizer for KCl, DTB crystallizer. So it can get very, very, very high. So we don't have any problem. We are not limited with capacity. It's the opposite. The crystallization really fits very well into very big capacities. Maybe the confusions get from the fact that some of the 2 references I'm showing has low capacities, has 50 ton, not low, but moderately low capacity, not very high, but we can really achieve very, very high capacities.
Great. Thank you very much for that, Sana.
No problem.
Just to be respectful of everybody's time, unfortunately, we've run out of our allotted time here, but I do want to remind you, feel free to send Sana an email if you think of any questions that come up afterwards. And for those of you, if we did not get to your question, we will follow up directly with you with that, for that. So. With that, that concludes our webinar today. We thank you very much for taking time out of your day to join us. And we do kindly ask that you fill out that survey at the conclusion of the webinar today. It should take no more than a minute or so. And for those of you that do, you will be entered to win the $25 gift card from Amazon. So if you are selected, we will follow up directly with you. And with that, that concludes our webinar today. Thank you very much.
Thank you, everyone.